When laser optics operate under intense laser irradiation, they might eventually suffer from damage. The damaged optical element doesn't work as expected and cause multiple troubles in various laser-based systems. In order to avoid unexpected laser damage, optical elements should be tested before use. How to survive laser damage? There's several possible methods, and one-on-one test is one of them. Let's discuss how the one-on-one test is conducted. The sample surface is divided into a virtual matrix of sites to be tested. Each test site is visually inspected under a microscope prior to laser exposure. An inspected site is exposed at fixed laser fluence, which can be adjusted by changing laser power. Power is usually monitored by the power meter. Let's mark different used fluence levels on the x-axis. Each tested site is exposed to a single laser pulse. After exposure, the status of the irradiated site is inspected with offline microscopy and interpreted as either survived or damaged. A fixed number of test matrix sites is irradiated by a single laser pulse at constant laser irradiation level. Then the probability of damage is estimated for a particular fixed irradiation level. It can be calculated as a ratio between damaged and all exposed sites. Let's mark damage probability on the y-axis. If all the sites survive laser exposure, the damage probability is estimated to be 0. Further, the laser irradiation level is slightly increased and another row of test sites is exposed again. Let's say 1 out of 5 irradiated sites was identified as damaged. The estimated damage probability is then 0.2 for used irradiation level. Following this algorithm, the whole sample surface is exposed to collect sufficient data. As laser irradiation level increases, more and more sites get damaged, thus damage probability increases. For a high enough laser irradiation level, all tested sites are expected to be damaged. The damage threshold is then estimated as the highest irradiation level featuring 0 damage probability. It is done by extrapolating damage probability with an approximate extrapolation model, either linear or nonlinear. As samples feature different damaged probability curves, it is also possible to interpret these data using advanced statistical models. Steeper damage curves usually mean higher defect densities. More complex or broken damage probability curves indicate the presence of different types of damage-limiting defects. This knowledge helps to use one-on-one results as quantitative feedback when optimizing polishing, cleaning, and deposition procedures in order to reach the best possible results. However, no technique is perfect. One-on-one procedure could overestimate LIDT in cases of low defect density or produce not repeatable LIDT values. Fatigue or incubation effects are also not considered here. Other test procedures must be chosen when investigating multiple or long-term irradiation effects, using one-on-one LIDT as a good reference. Nevertheless, one-on-one test procedure is still a good option to characterize defect-driven damage in cases of high defect density. Single-shot, time-on-one testing is also a popular use case scenario with continuous wave irradiation. Being a quick and easy-to-interpret technique, it is well suited for fast screening experiments, characterization of defect ensembles, studies of intrinsic material properties, or bulk damage. Contact Lidaris to learn more about one-on-one LIDT test and other ways to solve your laser damage problems.